don't want to be recorded. I don't know. Don't say anything. Go. That should work. All right. So, applied linear algebra. This lecture is mostly going to be on what do we do with linear algebra? Where does it come up in like most prototypical places? So, I'm gonna start out with like your most prototypical, imaginable, super applied engineering problem. You got a truss bridge. All right. So you got like a bunch of struts holding the thing together. They're going to be under compression or tension or what have you. And you've got some forces on the thing. So like you've got like some cars on it, putting some force over here. There's some wind, like putting some force over there. Of course, there's the weight of the struts themselves. And there's some normal forces from whoever's holding the bridge up, so on and so forth. Welcome. Grab a seat. So one like prototypical thing that we do in engineering when thinking about bridges like this is first we write down all the equations for the bridge when it's like static. Okay? So we'll take each of these components, treat it as a spring. So it's got like force in the spring. It's going to be roughly a constant times this position, x1, here's x2, and then take the length of that and subtract some sort of equilibrium length from it, right? So x equilibrium, and then that's like your standard spring equation, right? And then at equilibrium, that should work out to 0, or the sum of these things at each node should work out to 0. And you're going to get a bunch of equations like this. Okay? So our whole like bridge, when it's static equilibrium, is going to be described by this whole series of equations. And I'm going to be a little bit abstract here and just write all of our equations in the form 0 equals fi of x, and what notation I'm using? Let's say neighbors of. So here's what this means. So for instance, if we're looking at a particular node right here, this node is touching each of these 4 springs. So there's going to be an equation that balances the forces at that node. So that'll be our function fi. And the inputs to that function will be this x, this x, this x, this x, and this x. So we'll have 5 of the x's in that equation. Notably, this x won't be in there, and this x won't be in there. That's important as our systems get bigger. Like you can imagine, if we had to, if I refine this truss picture and just like add a whole bunch of more triangles to it. As our picture gets bigger, usually our equations are going to be local in the sense that any given equation only has a few x's in it. So like even as I get a more complicated truss, I still only have like, in this case, 5 x's in my equation in each individual equation. But I'll have more equations. Like I'll have an equation balancing forces here, an equation balancing forces there, an equation balancing forces there, so on and so forth. It's important because this is what's going to give rise to sparsity later on. We'll probably have a whole lecture or two on that. So anyway, we've got our equations describing this thing at equilibrium. And the supernatural thing that you do all the time in engineering with this thing is you look at the Jacobian, partial f, partial x. This is a matrix. What we're doing here is we're taking each of the fi's and we're differentiating by each of the fj's. So we're going to have this big matrix where like this entry is the derivative of the first f, so like whatever equation is balanced to 0 right there, with respect to x1. I guess if this is f1 and this is x1, that one's going to be 0. So that's great. And then here you'll have partial f1, partial x2. That one will be non-zero in this case, so on and so forth. And partial f2, partial x1, partial f2, x2, so on and so forth. So we're taking the derivative of each equation with respect to each of the variables. Okay? All right. And the main question I want to start with is like, what sorts of interesting things do we naturally want to do with that matrix? Like, what sorts of linear algebra operations do we want to do with it? And what do those operations correspond to on those original equations or in our bridge picture? Okay? All right. So, first thing is, well, you have a bunch of equations. Maybe we want to solve them, right? In particular, if we're using this matrix, usually in a context of solving the equations, we're using this matrix in the form of a first order expansion. So we've got 0 equals, I'm going to write it in the shorthand form, f of x. These are both vectors. That's f of some reference point x naught plus partial f partial x dotted with x minus x naught. I am pretty quickly going to be lazy here and forget about writing vectors on everything, but like, assume everything's a vector. I'm going to switch this to a superscript. There we go. All right, so what does this mean? Physically, in the case of the bridge, this means we've got a bridge, it's sitting there, and it's like stable. That's our x naught. We've got our reference configuration of the bridge.
But is it stable? How would we know that?
Well, we would know that because we took out our measuring tape and we measured all the lengths of all the struts, all the positions of everything on the bridge, and then we plugged all of those x naughts into our equations, and it said, those all balance to 0. Therefore, the thing was stable at x naught. But now we come along, and we're like, okay, I'm going to put some more forces on this thing. Maybe I have some cars on the bridge. There's a car there, there's a car there, there's a car over here. All right. Well, now, so I started out, I had f of x naught was equal to 0. But now I've got some additional forces. So I want to find the new x's under those forces. Well, all right. I'm going to assume that the bridge didn't move too much. We usually hope that that's the case for bridges when you put cars on them, right? All right, so I got f of x naught plus some small dx. I want that to be equal to my new forces, delta f. Make sense? So it should be, my dx should be balancing out whatever extra forces I put on this thing. All right, well, we use our expansion here for f of x naught plus dx. Here's dx. F of x naught is 0. So what we get is the delta f is equal to partial f partial x dx. All right. Now this is like where your typical matrix inverse problem comes from, right? We're trying to find some dx's that we can multiply by this matrix such that we get df. Notice I have not actually said here that this matrix is square. This is not necessarily a complete set of equations. We may only be looking at a subset of equations for this bridge, and that's totally fine. That means like whatever dx's this bridge settles into, there will be some, like it's a bridge, there will be some unique set of dx's that it settles into, presumably, right? But we may only have incomplete information about those dx's. We may only be able to take some directions of them from the equations we have, and there may be additional equations that we would need to solve the whole thing, and that's fine. All right, so that's use case number 1. Use cases.
When you say it's fine, even though it's underdetermined, you mean like you could do a pseudo inverse, or what do you mean?
We'll get to that.
Okay.
So first use case is we want to solve equations like f of x equals 0, and that gives us matrix operations like invert or partially invert, square codes, df dx. All right, now we've got the obvious one out of the way. Somebody tell me something else interesting we might want to do with this matrix.
I want to know small perturbations are stable.
Small perturbations are stable. That's a good one. All right. What does this mean for the bridge? First, I'm going to draw a picture. Suppose, so we've got this giant system of linear equations represented by the matrix. Let's imagine that we're in 2 dimensions. And I've got like one line that looks like this and one line that looks like that. I'm trying to find their intersection point, right? And an interesting question I might ask about this problem is if I wiggle this line a little bit, how much does that change where the intersection point is? So if my 2 lines are very nearly parallel, and I wiggle one of these lines a bit, so I wiggle this one down to there, that solution point is going to move a lot. Like I did this relatively small wiggle and my solution jumped way the hell over here. That's extremely sensitive to perturbations. On the other hand, we could imagine that my lines look like this. They're practically orthogonal, so when I move one of them by a little bit, the solution only changes by a little bit, right? From here to there. That's very stable. All right, so this is, first of all, notice it's a property of the lines, or of the linear equations here, so it should be a property of this matrix. So if we're doing like some sort of equation solving thing, for any small changes, we can talk about how much bigger the small changes to the solution are when I make a small change to the forces. Right? So we should be able to compute it from this matrix. So what sorts of, anybody want to tell me what operation we would do on this matrix to get some idea of this?
Is it the like maximum of the eigenvalues?
Close. You're on the right track. I have some bad news for you about this matrix, though.
Right, it's not square.
It's not necessarily square.
Oh, singular values.
Yeah, there we go. Singular values. So singular value decomposition. I can take this matrix and write it as a rotation. Technically, it's like an orthogonal matrix. We can choose it to be a rotation. I'm usually just going to say rotations in this context because it's more intuitive that way. So we've got a rotation times a diagonal matrix times another rotation. Right? And if this matrix is non-square, so like maybe this matrix is, which way am I? This way. I've got a lot more variables than I do equations, then this will be a rotation on the variables. So it's going to be a pretty like high dimensional rotation. This will be a rotation on the equations, so it'll be a lower dimensional rotation. And somewhere in there, there's a projection. So this thing is not actually diagonal. You can picture it as like diagonal and then a bunch of zeros out here or something. Or equivalently, you can just say that we're chopping off all the bottom rows of this rotation. All right. Why is that a useful way to think about this? Well, if you think about what a rotation does to these lines here, it doesn't really change how sensitive a solution point is to the equations, right? If I'm just rotating this whole thing, the picture is still going to look the same for purposes of this sensitivity, right? What does change how they look is that stretching thing. Well, I haven't actually said that this is stretching. Diagonal matrices, they do stretching. So for instance, if I'm starting with a picture like, I'm starting with a picture where like these things are basically orthogonal, I'm happy where we don't have a lot of sensitivity, but then I stretch it this way. So I'm doing a big stretch in the y direction, and then I'm compressing it this way. I do a big compression in the x direction. Well, now my lines are going to look like this. So now we're back to this extremely sensitive picture where like if I shift one of these lines a little bit wrong direction, like I shift this one this way a little bit, all of a sudden, boom, my solution shifts like way the hell over there. So when I'm looking at this singular value decomposition, I can look at the singular values, the guys on the diagonal here, and if I see something that looks like, oh, I'm doing a lot of stretching in one direction and compression in another direction, or like one of them is stretching a lot more than another, that's telling me that these equations are going to be very sensitive in that sense. Make sense? All right, so that was use case number 2.
So wait, do you care about the magnitude of the stretching or the difference between like the two stretchers?
Good question. If you look at this picture, imagine I'm stretching it the same amount in both the x and the y direction.
Nothing changes.
For sensitivity purposes, nothing changes. So I mostly care about relative stretching along different directions.
What would this solution robustness, I guess, correspond to in the bridge case?
Good question. In the bridge case, let me get a good picture here. All right, I want you to imagine for a sec that we're over here where we're solving these two lines. What's actually going on is that I have two physical pieces of metal, and there's like a little, they're crossed, and there's a little ring at the spot where they cross. And I'm physically moving those two metal rods so that the little ring will end up wherever they cross. And if they're very nearly parallel, and I move those two metal rods a little bit, that ring ends up way the hell over here, right? Or another way of picturing it in the bridge maybe I have two forces that are very large but very well balanced, right? And now, like, actually, no, that's not a good example. Let me think of a different one. I have, better one. Okay, I have two girders which are like very nearly parallel, and the forces are balanced. If my forces shift a little bit, then like my forces shift a little bit so that this is no longer balanced. Then you can imagine, because these two are like so close to being aligned, if there's like a force along that way, you're going to see something like slip a lot this way. Does that sort of make sense?
Yeah.
Yeah. Okay. So that was use case 2, is sensitivity. Sensitivity of solution.
We're measuring the alignment of the girders.
Yeah. in a surprisingly literal sense, yes. So that gives us the SVD of, and we'll see other things that the SVD can tell us later on. All right, give me another one. What else? What other interesting questions would you want to ask about the bridge and/or this matrix? Yes.
I may want to know if I add another thing. If I connect two components here, how much better is what changes am I gonna expect for like the differences in the bridge?
There we go. All right. So let's say I add some extra component to the bridge. We can think of this as like adding a constraint or like adding a piece somewhere in there. How's that going to update this matrix? I guess it's usually going to add a row. Bingo. So actually, sometimes going to add a row, it also sometimes adds variables. So that's important. Yeah, that's basically it.
Oh, cool.
That's the. I was about to go into something else, but this isn't actually that good an example of something else. So yeah, that's basically it. It'll add some rows, maybe some columns.
Can you look at the null space to see what like forces you can add that don't change the equilibrium?
There we go. Two ways of looking at that actually. We can ask, what forces could I apply that would leave the bridge and that would not move the bridge? I can also ask, these forces are balanced, but maybe the bridge still has some degrees of freedom. How can it move, right? And like you said, the way you look at that is you look at the null space. The null space on one side is, we'll call it the force side, or the equation side, is going to tell me how I can change the forces such that the bridge stays in the same place. The null space on the other side, we'll call that the position side, or the x side, is going to tell me how the positions can change while still being in equilibrium.
So it's still in equilibrium because in the special case we're looking where the forces are 0.
Still in equilibrium. Say that again?
Wait, it's like without, you said it's still in equilibrium, that's because the forces are balanced in this case. You could do the same thing if it weren't in equilibrium, right?
Yes. So even if it weren't in equilibrium, you could have like different positions yield the same forces. Yeah. All right. And practically speaking, what was that?
Your bridge might have problems with the thought equilibrium.
You know what? Tell you what. My bridge has some little wheels so that it can slide sort of back and forth
It's a canal
along the
canal bridge.
Yeah, exactly. It's great.
It might also be a steady state. It doesn't need to be in equilibrium, right? It could also be just swinging. That's still fine.
I would prefer a cross bridge to not be swinging.
Okay. If you talk to engineers who do bridges, they're very sensitive about the swinging thing. There's one particular bridge.
The Comanero's bridge.
Yes.
Yeah, the nice residence.
Yeah.
I want to hit my bridge with a hammer and see how it rings.
Hit your bridge. Now we're going to get to that one later.
Okay.
We're still on statics for now. Dynamics are later.
Wait, what, am I in a physics lecture?
We're learning about matrices.
Okay, cool. No,
Yes.
Sorry.
The topic is applied linear algebra, so we're talking about what the fuck you do with linear algebra.
Sounds good.
I want to see if I can remove any truss pieces without losing anything significant.
Wait, but we
Because I
didn't
want
discuss
to
the
be-
null space
Oh,
of the other things.
Right,
I
yes.
wanted
We're
to
still on
discuss
how do you actually compute the null space? And like how do you represent these degrees of freedom?
And also, why is one side of the force like null space and the other? Or like, why is can you just like put it from one side to the other just fine? Like it's a different set of equations.
All right, let's write this out. We're going to be using the SVD again because it's the wonderful tool that we use for everything. So we calculate our SVD, and we find that a bunch of the singular values are 0. What does that indicate? It indicates we have a low rank representation of this matrix, right? You can think of it as there's a relatively small number of columns over here times a relatively small number of rows over there, and you multiply those two matrices together to reconstruct this guy. Conversely, that means that there's lots of directions on the x side that are orthogonal to those, and lots of directions on the f side that are orthogonal on this side. And we can move in between those two by looking at, like, there's going to be a correspondence between each row over here and each column over there. Like each row on the x side has a corresponding column on the f side, meaning that if I move my bridge a little bit along that direction, so I'm moving each of these nodes a like proportional amount in order to move along that vector, then I will get these forces. And I can do that, I can sort of combine vectors that way, and the forces will sort of combine independently of each other, conceptually speaking. This is kind of a weird thing to visualize in the case of a bridge. It'll be more natural when we get to second order expansion a bit. But anyway, then to calculate our null space would be like, okay, the null space is everything that's orthogonal to these guys on that side, or to those guys on this side. So degrees of freedom.
Wait, aren't both the rotations full rank in the SVD?
No, so in an SVD, there's like more than one way of writing the SVD, but generally speaking, if you have a bunch of 0 singular values, then like you could write the rotation matrix as a full rank thing, but then a bunch of those rows are going to be multiplied by the 0 singular values. So usually it's more convenient to just truncate all those things that are being multiplied by 0, especially because they're all being multiplied by 0, you can sort of take arbitrary linear combinations of them. So it gives you this annoying degree of freedom that you don't want to deal with that shit. This actually brings up an important point. Pro tip: in numerical libraries, let's say I'm using NumPy. Call numpy.linalg.svd. Very important, when you pass in this matrix, you also pass in full matrices equals false. For some reason, I don't know why these libraries default to passing you these like giant ass matrices, even though you have a bunch of singular values, but they do. And it's really stupid. They really shouldn't do that.
It's probably easier, I guess.
I'm sure there's like some excuse for how it's easier for someone somehow, but like it just sucks up a ton of memory and you really don't need any of that.
I mean, the advantage is you have a predictable shape. So like if usually your matrix is full rank, then maybe it's just easier to assume that it has full rank in all of the rest of your code.
Okay, I'll give you some credit for that answer.
I've used non-full, or I've done this with two before, and like, what's worse than not knowing what shape your matrices is gonna be is having your RAM filled up with a bunch of useless numbers.
Yeah, they are useless most of the time. The application then clearly is bad. Yeah.
And I guess that's a good case for like failing loudly. Like if it fails, like if your matrix, you expect it to be full rank, but then it's not all of a sudden, you actually want an error message or something.
Anyway, there's one more use case I want to cover here. You brought up removing struts.
Yeah,
That's
steel's really
what-
expensive.
Was that?
Steel's really expensive, and I want to skip on some of these lines.
Yeah, okay. We'll get to that use case when we get to talking about optimization later. Okay. Not today. Yeah. The other main one I want to cover is oftentimes for whatever particular thing I'm thinking about with this bridge, I don't actually care that much about what lots of these variables are doing. So for instance, maybe I'm the guy in charge of like designing the points where the bridge gets secured to the edge. And I need to worry about like it's going to be loaded with cars and whatnot. But I don't particularly care how all the stuff in the middle is moving around. I just need to know how I need to secure it to the edge, right? So natural thing I might want to do is just like eliminate a bunch of those variables from my equations. All right, solve those out. What's the corresponding operation for this matrix? The one person who's seen me do a lecture on this before. Go ahead.
Sure complement.
The sure complements. All right, good. So here's how this works. We're going to take our matrix to erase all the explicit stuff in there. We're going to take our matrix and we're going to break it up into some blocks. This block is the variables we care about. Or sorry, these columns are the variables we care about. The bears we want, and these are the bears we don't care about. Bears we don't care. And then similarly over here, these are the equations we care about. And here are the equations we don't care about. All right, so what we want to do is use these equations to eliminate these variables. Note that does mean that this submatrix right here needs to be square and invertible, because like that's the part that we're going to be using those equations to eliminate those variables. So like that has to actually be solvable and it has to like fully eliminate those variables, right? Okay. Usual way to write this. This is A, B, C, D. So we've broken up our matrix into those blocks. And the sure complement is A minus the dimensions right here, B, D inverse C. And what this tells us is if we took our original equations, eliminated these variables using those equations, and then did the linear expansion, we get this guy. So it's the sure complement. And that would tell us how the remaining variables vary with the remaining equations. Sorry, other way around. How the remaining equations vary with the remaining variables. Make sense? And when you're doing numerical linear algebra, you'll find that this guy pops up all over the place. It's actually kind of entertaining because like people who do numerical stuff run into this guy all the time, and they're just like, man, I have no idea where this guy comes from, but it sure does come up all the time. And the reason it comes up all the time is because they're eliminating some variables. So that's use case number 4. Okay, how are we doing on time? What time is it?
7:52.
7:52?
30.
Oh, 32. Okay. All right, I'm less surprised now. Let's see. Cover here. All right, I think that's going to be it for the bridge example. Any questions on any of that so far? Cool. Let's move on to a different class of use cases then. So this class of use cases was all, we have some equations, and we do first order expansion. The next class of use cases is going to be, instead of a set of equations in many variables, we're going to have one real valued function with a bunch of variables, and we're going to do a second order expansion. Okay? So the thing to picture here, in one dimension, it would be like we have some function like this. We're going to think about what it looks like near the minimum. Near the minimum, it looks sort of bowl-shaped. We're going to take a second order expansion to talk about sort of how curvy it is. In multiple dimensions, it may have like different curvature along different directions. So you can sort of picture like it's sort of narrower along this direction and longer along that direction, or like a rotated version of that sort of thing, right? We're going to be doing a second order expansion to talk about its shape. A more practical way to draw it, 2 dimensions, is here's x, here's y, and I'll draw something like this to indicate level sets of the function. So like it's sort of going up very quickly along here and going up very slowly along there. Make sense? All right. So first of all, the expansion by which we represent this, we've got our real valued function. Does anyone have a request for what letter we should use for the real valued function? There we go. That's one I was expecting. All right. Anyone else?
R for real.
You're disqualified. Was that? No. All right. We already used F over there. I like F for like systems of equations. So I'll usually use either phi or u for a single dimensional output. U would be if we're thinking of it as like a utility function or an objective function. Phi is how physicists write utility functions.
Is it like potential?
Yeah, I mean, it's electric.
Potential functions and utility functions are the same thing.
Well, also we also use U for potential energy.
Well, yeah,
Which I
that's
think
true.
is probably the older version than utility.
Yeah, that's probably true. All right, fair. So anyway, we've got our phi of x, where x is a vector, phi not a vector, that's just a scalar. And if we're taking like a full Taylor expansion, we'll have phi of x naught plus partial phi partial x, evaluate at x naught times delta x, plus 1/2 delta x transpose partial squared phi partial x squared evaluate at x naught x. We'll mostly be thinking about the case where we're right at the minimum or at a local minimum. So that means the gradient is 0. We don't have to do that when we talk about Newton's method. We won't make that assumption, but that's mainly the picture we'll be drawing for now. So the main matrix we're going to be interested in here is this guy, the Hessian, the second derivative of phi with respect to x. So that guy looks like, for instance, in this case, it would be second derivative of phi with respect to x, a mixed derivative of phi with respect to x and y, that same mixed derivative over here, x, and your second derivative with respect to y. And of course, as we go into higher dimensions, this will just get bigger. All right. First of all, I'm going to make an observation about this matrix. Because the second derivative of something with respect to x then y is the same as the second derivative with respect to y then x, this matrix is symmetric. All right. Anybody want to tell me something interesting and useful about symmetric matrices?
They're the best.
Diagonalizable.
Positive semi-definite?
They're not. It's not necessarily positive semi-definite. We'll get to that momentarily. But yes, the nice thing about symmetric matrices is you can always do a nice eigenvalue decomposition. So you've got your U. Okay, I'm gonna go ahead and write it as s squared. U s U transpose. Why am I writing this as s squared?
Because it's always positive.
It's not always positive.
Nope. Okay.
When
Can I give it?
it was real value.
All right. I'm gonna save that as a surprise then. Alternatively, you guys might be
Because
more
your
used to
singular
writing it
values
like
are the
this.
derivative of the eigenvalues.
There you go. That was it.
Not all the eigenvalues have to be positive, do they?
They don't, in general. We're about to make the positive semi-definite assumption.
Yeah, they definitely have saddles here.
Could be
Yes.
symmetric.
No, they can't. It's symmetric.
Wait, yeah, you're right.
Your eigenvalues can't be.
Okay,
Wait.
we'll get to it.
Okay.
So in general, if you have a symmetric matrix, you can always write it as rotation, then diagonal matrix of your eigenvalues, then the same rotation transpose. Yeah, they're very nice. You don't have to worry about like one of those. You don't have to worry about your matrix being like this horrid thing. This matrix does not have happy eigenvalues. Its eigenvalues very, very sad. You don't have to worry about that with symmetric matrices. Physically, what does this correspond to? What does this fact about eigenvalues mean in this picture?
There are like a number of like the singular values are like going to actually be orthogonal when you like picture it.
So in this
And, like-
picture, we've got these level sets are roughly elliptical, and we can look at the primary axes of the ellipse, which are easier to understand visually than mathematically. They're those things. Those primary axes of the ellipse will always be orthogonal to each other. That corresponds to the eigenvectors all being orthogonal to each other. And then each of them will have a different size. That corresponds to the inverse of the eigenvalue.
They don't all have to have different sizes.
Okay, some of them may have the same size. Like in general, they'll have a bunch of different sizes.
It's full.
Yeah, we'll get to that. So the important conceptual thing here is that like you can picture this eigenvalue decomposition as telling you about the shape near of the peak or the trough near a maximum or a minimum, right? It's telling you how wide it is along different directions, how narrow it is along different directions. All right. Somebody get the thing about saddle points out of the way.
Saddles are cool. I like them.
Objectively wrong.
If you can sometimes have eigenvalues of different signs.
There we
They're
go.
not the saddle point.
All right, cool.
That means it's hyperbolic. That means you have interesting dynamics.
So what you could have is this thing. What you could have is like a parabola that's sort of there's our two principal directions. Maybe we have a parabola that's sort of downward facing along this direction, but upward facing along that direction, and then we've got a saddle point. So it's going like upwards along here and along there. Sorry. Well, I just did not draw the thing I said I was going to draw. Directions are that way now. It's sort of going upwards along this axis and downwards along that axis. And then you'll have like some positive values and some negative values for your eigenvalues. We're mostly going to assume that away. There are like, analytically, there's interesting use cases for that. Numerically, we're usually interested in this case. Not like strictly always, but yeah, this is definitely the most common case.
I'm guessing you're also assuming away marginal eigenvalues.
What are marginal eigenvalues? I
Zero.
assume okay, zeros. Yes. We are not going to assume away zeros.
Zeros
we'll
can
allow
do cool
those.
things too.
Yes, they sure can.
Are you going to assume that you can't have zeros that make saddles?
What?
If you have like a fourth order.
Right.
correction,
Fourth order
you can
corrections.
have-
Yeah, we're just going
Yeah.
second order corrections.
Well, yes.
We don't care if it's a saddle to fourth order.
Okay, so you can have saddles. Then.
Sure. To fourth order, but not to second order. Anyway,
I think you don't want that.
I mean, numerically, it would be weird to find one. Because, all right, we're way off track. But it would be hard to tell if you were there, which is why I'm allowing it. Right. So, first interesting use case is like, we're near a maximum or a minimum, and we want to talk about the shape of that peak or trough. Why would we want to talk about the shape of that peak or trough?
This looks like pictures I saw in my differential equations class. So,
There you go, that's one. So, some reasons you might want to talk about the peak or the trough.
oh, it's orbits.
Orbits, there we go. So in physics, a lot of the time we have dynamics where like things are oscillating in here in ways that like decompose nicely along different directions of the trough. So for instance, maybe we have a ball rolling around here. That's not a ball. Sorry. A ball rolling. Someone draw me a physical way that a ball would roll here.
I mean, you could just.
You know what? It's rolling back and forth. Go very simple. No, we're not in phase space. It is rolling back and forth in a physical bowl. Yeah, so you have a ball that's rolling back and forth, and like, yeah, you can, since this is like an even, what do they call it, an iso level, yeah, it'll like always go to the same height of the
I'm kind of trying to work out what's
Right,
going
yeah.
here.
And if you have this ball rolling around in the bowl, we can typically like decompose its motion into motions along these two directions independently, and then like solve those out separately. Mostly we're going to talk about that when we get to dynamics, but yeah, that's the thing we can do. In neural networks, people say neural networks here. Anybody know anything about it? No, never heard of it. Okay, cool. Well, we'll cover some briefly just in case it's interesting. So in neural networks, a thing that gets talked about pretty frequently is how broad a peak is, or how broad a minimum is. Because when you're optimizing these things, sometimes you have some like crazy looking loss surface, and typically we expect that you're much more likely to fall into a very large, broad minimum rather than a tiny little minimum, right? Well, if you want to talk about how large how broad that basin is, simplest tool that you start right out with is you do the second order expansion and you say, okay, how big are these eigenvalues?
It's a very rough approximation in high dimensional spaces.
Works better for transformers, happily. They're much more. Anyway, so like how broad are the peaks, and then also along which directions. So like along some directions they'll be very tight, and that means your optimal parameters are very precisely determined along that direction. So in this picture, Along this way, we have like very precisely determined optimum. Along this way, it's less sensitive, so your parameters are like less tightly determined along that direction. This is also, like even before neural networks, this is how you would talk about this in statistics. So like if you're building some sort of estimator or something, you would talk about how broad your peak is in the loss landscape. Like they already had the idea of a loss, right? And if it's very narrow along some directions, then your estimate is very precise along that direction. So, use case. All right. What else? What else would we want to do? What other use cases do we have here? Interesting things do we do with this guy? Yes.
If we want to get a particular value, then we could invert it.
Like where you're going with this. Why would we want to invert this thing?
Find zeros.
So
Aren't we already at a 0?
we did assume that, but we assumed it, so we could relax that assumption for a minute. Suppose we're not quite at a 0. Maybe we're doing some sort of numerical optimization thing, and we just start at some random point out here, and we want to find the 0. Well, how would we do? So now, going back to our expansion here, our gradient is no longer 0, but we want to find a spot where the gradient is 0. So the equations we're trying to solve are going to be partial phi, partial x, delta x plus gradient 0. So this will be x squared. That's where. Yeah. So this is the equation that you would solve if you're trying to get a linear or quadratic estimate of where the minimum is based on a second order of expansion around here, right? And then we're back in this land. We have a bunch of equations, and we can do all the usual stuff that we do with a bunch of equations. Notably, we still have the sorts of things that we had before, where we want to think about like sensitivity or variable elimination or degrees of freedom. All those things carry over to this use case now, where we're doing optimization of a variable. In particular, a big place where this comes up is if you're doing something like gradient descent, for instance. If you're doing gradient descent on a function which looks like this, so it's like very narrow along one direction and wide along another, gradient descent has an annoying tendency to sort of bounce back and forth. It's very inefficient. It doesn't go very directly towards the middle. If you use something better than that, like say conjugate gradient, then first you sort of jump down to somewhere close to this main axis, and then you do a jump that's orthogonal in the eigenbasis, which means you're basically jumping straight along this axis, more or less. And that's like the sort of standard explanation for why conjugate gradient methods will converge a lot faster than a gradient descent method. Yeah, so that's another use case. And then again, it's like the eigenvalues that you care about here. What else?
I mean, if we're talking about second order, I mean, using second order components for optimization, the direct one would be second order optimization, right?
Yeah, so the direct solver would be we just directly invert this matrix in order to solve these equations. So that would correspond to this guy right here. You know, you're solving a set of linear equations, you want to invert the matrix. Yeah, in practice, that tends to be painful because matrix inversion is O of n cubed.
And you can approximate that with like LBFGS.
All right, we're gonna have there's gonna be a whole lecture on this, but with approximate matrix inversion methods, the majority of them work in one of two ways. Either they're doing something conjugate gradient like, and conjugate gradient is very special in that you don't have to keep around increasing amounts of stuff as your approximation gets better, or they're doing anything else, and then you have to keep around increasing amounts of stuff as your approximation gets better. Yeah, we'll talk about that. So the important point for now is we have the use case of optimization, and that brings us back to all the same questions we had for that guy. That's all the things I wanted to talk about for second order expansions. Anybody have any others that I should throw up there? Other use cases here?
I kind of want to do perturbation theory, but you probably don't want to. Let's
No. We are going to do a different dynamical systems example, and then we can talk about
Yeah.
perturbation
We
theory.
have an RL paper I can't read because it's got some perturbation theory. So if you can explain this to me sometime, that would be great.
Sure.
Perturbation theory is actually very easy. It's just linear algebra.
Cool. Except for when it's not.
I don't want to know about this.
When it's not linear algebra, nobody does it.
I
Because
disagree.
it's just extremely painful.
As someone who has done it, I disagree.
I'm sorry for your suffering. I hope it was worth it.
It was. This is beautiful.
Okay, cool.
Continuous spectra are wonderful. You should use them all the time.
What was that?
Continuous spectra are wonderful. You should use them all the time.
All right. Other use case together. How are we doing on time?
7:54.
7:54. All right. Yeah, we're gonna speed run the last couple bits. So last two examples, we have dynamical systems. So this is either something like x of t plus 1 equals some function of xt, or something like dx dt equals f of x of t. And of course, everything's vectors except for t. No vector t. Don't you start.
I don't play with that.
You're not even arguing with that. All right, cool. And of course, as usual, we want to do first order expansions on these things. So like, we've got some fixed point, x naught, and then we're thinking about the dynamics near that fixed point. So you've got x. All right, and the idea, the point of having a fixed point here is that we can just sort of ignore it. Similarly, over here, you would have some f of x naught, where x naught is a 0 point, 0 plus whatever. And generally speaking, the sort of equation that we get out of this is something like, I'll just focus on the continuous case for now, delta x naught equals some matrix partial f partial x times delta x, right? So I get this nice linear dynamical system. All right, what's the most obvious thing that you could possibly want to do with that? Solve the differential equation or the recursion. All right.
Draw pictures of the solution.
And what sorts of things might we learn by solving this? So, like, reminder, these aren't the actual equations we care about. The actual equations we care about are these nasty nonlinear things. So what sorts of things are we going to learn by solving these linearized equations? Yes?
What things look like pretty close to where you already are?
What things look like pretty close? All right, that's a good start. So I'm starting with, here's my space X, and I've got some, I'm setting myself to some point where I don't move. Either it's a fixed point in the discrete time case, or it's a point where it's stable. And then around that, I've got some dynamics. Here are some things it could look like. Maybe this point is unstable, and I just go flying away from it, no matter what. Or maybe the point is stable, and I always go flying towards it, no matter what. Or maybe it's a saddle point, and I tend to go flying towards it along one direction, and then get pushed away along another direction. Or maybe I tend to go in circles around this point. Those are all possibilities. Those are all possibilities for like what this thing could look like near that point specifically. How do I find out which of those possibilities I'm in? Yes, good. So a standard way of finding that out is we're going to take the eigenvalues of this guy. On typical cases, if all of those eigenvalues are negative, then you're always going towards it. If all those eigenvalues are positive, you're always going away. If the eigenvalues are imaginary, then you're going in circles around the point. So this is like perturbation theory 101 for dynamical systems. Yes, person who looks vaguely confused.
I haven't done imaginary numbers in a long time because I did computer science like a fool, and so now I'm just trying to work out how circles work. I've got no idea.
Circles? Oh no.
That's not an integer. I don't know how to.
Well, I sure hope we have a lecture on that later, so you'll know how that works.
You better be careful. I might just grab this teaching opportunity before you get there.
Nope,
It's
nope,
super
nope.
exciting.
We're going to finish in a timely fashion.
Well, no, okay.
Timely. And then you can go.
Someone said learn things about numbers.
Yeah. think you may get a little lost if you go all the way into things. All right. Yep, that's it. That's dynamical systems in a nutshell. There's definitely nothing else to say about dynamical systems. All right, fine. You can name one other thing I should put on the list.
I mean, bifurcation theory is pretty cool, although it's not linearized.
That's okay. That's a solid case.
I mean, it's still higher rank.
I mean, this is still the basic tool you use. All right, I'm gonna leave it for now.
Jokes.
Okay, and then last thing we'll briefly talk about is covariance matrices and linear regression and that sort of stuff. So this is the only case we're going to talk about where the thing where the matrix we're dealing with is not df dx. Instead, the matrix we're talking about is a matrix of data. So we've got like, how do we want to write these? Maybe x1, x2, x3, and this is going to be some other variable, y1, y2, y3, so forth. So we got this big old matrix of numerical data. What do we want to do with it?
Fit a line.
Fit a line.
I want to figure a neural network.
What?
I want to fit a neural network.
Later.
I want to do SVD.
All right, so hold on, we're still on fitting a line. After that, we're going to take an SVD.
I want to take a continuum list.
I like that. All right, so first obvious thing you might want to do is some sort of linear regression, right? So you've got like some thetas, and you're trying to find coefficients for each of these data things, such that I need a name for the variable you're fitting to. I want to call the variable you're fitting to.
Data.
Z.
Z? Okay, I guess I haven't used Z in here yet.
Wait,
We're going to pretend there's no Z in this matrix.
Wiggle.
Okay. So you've got all your observations of Z, and you're trying to use this data to predict Z. So you're doing a linear regression and finding those theta values. And of course, that means we're doing something like inversion on this matrix. Obviously, it will usually not be square in this use case, and that's fine. Do weird sorts of inversions. All right, now on to the more interesting one. Who said SVD? Good. What will an SVD tell us here? Let me first write a linear regression.
SVD will tell us how the different data dimensions are related.
How the different which dimensions?
The x, the y, and then whatever letters we use.
And then whatever letters aren't Z. Yeah. Good. All right. So taking our USB thing, some different ways we could interpret this. One thing we very often see is that our singular values drop to near zero very quickly. So we could say like, all right, approximately there's only a dozen non-zero singular values, and then everything else is zero, which means we have a low rank approximation here. How do I interpret that?
A lot of the data's fluff. I need it.
You could say that a lot of the data is redundant. A way that I would say is not quite that it's redundant, but that a lot of these features are sort of measurements of the same thing in some sense. So like maybe I have a marker, and I'm measuring the length of a marker with a measuring tape, and then I go grab a ruler and I measure the length of the marker with the ruler, and then I go grab some really big calipers and I measure the marker's length with the really big calipers, and I'm just recording all those as different data points. And then I go do the same thing with some other object. I get the eraser and I'm measuring the length with all these three different things. And then I would expect to see this happening where like we have this relatively low rank decomposition because I've sort of made a bunch of different measurements of the same thing. Makes sense? This is another thing that we'll talk more about in a future lecture, but like in general, when you have a low rank decomposition, you can think of that as conceptually our variables sort of factor through some lower dimensional thing. So in the case of data, it's saying that a bunch of this data is actually just measuring this smaller number of actually independent things a bunch of times. Yeah. All right. That was the main thing I wanted to say about data. Anything else people want to hear about data matrices?
I know, like, there's this Karma trick which is popular in support vector machines, where like you take the inner product of a bunch of stuff and then magically you get out like classifications of your data.
Yep. there is.
That's the thing you could do.
Yep, that's the thing you could do.
Let's look at the covariance, which would then be related to the SVD.
Yes, you can look at the covariance. Similar concept there. If you have a covariance matrix here, the important thing is that now it's square. And then you can do broadly similar type of decomposition. Square and symmetric. And then, as before, once we go to the square and symmetric case, we get very nice happy eigenvalues. And you can interpret it in broadly the same way. One more thing I would say about a covariance matrix, a thing you very often have is some sort of like graphical structure out in the world. So this would be like, you can think of this as a causal model. So like, say this variable, all the variables are sort of connected, but most of them don't directly interact with each other. So this one only interacts with that one via those two, right? So there's this graphical structure here. With a covariance matrix, if you take the covariance matrix of all these variables, you can then take the inverse of that covariance matrix, and that should be approximately sparse, with the non-zero entries in that inverse covariance matrix corresponding to the interactions in this graph. Yeah, that's pretty cool. Why would a weird thing like that happen? I don't know. Maybe we'll see more of it later. So you can back out locality / causality inverse. That's all on.
Would that be causality or correlation?
What was that?
Correlation.
Yeah. Once you get to more than two variables, you can back out causal structure from this graphical structure. This is like Perl type stuff.
Like, not always. Sometimes you can.
Sometimes, yes.
And that usually also relies on a lot of assumptions that you need to make.
At the end of the day, with causality, usually the part of it that's actually important in the first place is the graphical structure. The directions of the arrows is kind of like less important. But yeah, that's a thing we'll get to when we talk about sparsity. That's it for today. Anything else before we wrap? Everyone know what use cases of linear algebra are now? Ooh.
Yes, now I know all of them.
Yes, literally all of them. There are no other applications. Definitely the physicist sitting next to the mathematician, between the two of them, don't know any other applications.
Also, perturbation theory is not just a split.
Yeah, that's true.
You can do perturbation theory on algebraic equations.
That's true. Cool. We're done.